A hash-based message authentication code is, as the name indicates, a message authentication code, and as a system is a construction based on an underlying cryptographic hash function that can be chosen to either be message access5, SHA-1, or SHA-2. As a message authentication code, the use of HMACs to provide authenticity to messages relies on the availability of a symmetric key. In order to calculate a MAC tag for a given message and a given symmetric key, the symmetric key K is first XORed with the constant hex string 0x3636, with the result of the XOR then concatenated to the original message, with the result of this concatenation then fed into the chosen hash function to create a first hash value. The symmetric key K is also XORed with a second constant hex string 0x5c5c, with the result of this XOR then concatenated to the previously calculated hash value, and with this last concatenation then again fed into the underlying chosen hash function, with the resulting hash then being the MAC tag for the message under the symmetric key K. This sounds interesting, so it's time to get into the demonstration on how to implement the HMAC straight from the official NIST specification, which will also allow to understand why, for example, for SHA-2 with 256-bit hash values, the recommended maximum size of the symmetric key used is 512 bits. Hash-based message authentication codes, HMACs, are defined in the NIST FIPS publication 198.1. This NIST publication is quite a short specification, and the specification of HMAC can be found in Chapter 4, and its description fits on a single page. In order to drive the implementation of the NIST specification, I again fell back onto the official NIST test vectors as publicly provided by the NIST Cryptographic Algorithm Validation Program. These NIST test vectors are all contained in a single text file, and I pre-chose 3 test vectors for HMAC SHA-256, the reason for which will be clear later on. The tests to write in this driver are clear. For each NIST test vector, a key and a message are provided, and the HMAC implementation needs to calculate a MAC tag that matches the MAC tag expected and provided by the NIST test vector. With a dummy HMAC function returning an empty string, all the test cases failed as desired, and the stage was set to proceed to implementing HMAC. Implementing HMAC was then a translation of Table 1 provided in Chapter 4, which indicates that HMAC may be a 9-step process. The first 3 steps are a comparison of the key length with the block length, if the key length is the block length, then the initial key, K0, is just the key provided. If the key length is larger than the block length, then the initial key gets hashed with the specified hash function, and the result padded with 0 bits in order to be of the same length as the block size of the specified hash function. If the key length is shorter than the block length, then the initial key is just padded with 0 bits, such that the result is of the same length as the block size of the specified hash function. Steps 4 to 9 I then combined into one statement, and by defining the IPAD and OPAD constants as provided in Chapter 2.3 of the specification, and by defining an XOR on bytes function, the HMAC implementation was complete. Going back to the driver of the implementation with the 3 NIST test vectors and running the driver then indicated that the implementation, at least with respect to these 3 test vectors, was a correct implementation of HMAC. With this specification of HMAC, it's now also clear as to why, for example, for HMAC making use of SHA-2 with 256-bit hash values, the recommended maximum size of the key is 512 bits. This is due to SHA-2 with 256-bit hash values having a block size of 512 bits. If the key used with HMAC and this underlying hash function would now be larger than 512 bits, the key would first be hashed and then padded with zeros. To avoid this, a key of length at most of the block size of the underlying hash function should be used.